Hi folks, thanks for coming today. We have an exciting night today, and we have with us our special guest, Amir Husain, and he doesn't need an introduction here. He's one of the chief, basically the AI visionary in Austin. He's from Austin, and so we'll get started. Just before that, I will go through our regular intro in terms of our logistics and next meetups and stuff. So bear with me, but we'll get started very soon. And also, please help yourself with the food and drinks sponsored by SparkCognition. So help yourself there. So the first announcements are we have a couple of meetups coming up. We have two subgroups formed already. One is this related to ML deep learning study group. We're at the chapter 7 for that book, and we're doing it's going pretty good. So that's one of the. If you're interested, please join that, and we have the next meetup coming in August 17. Another one we just got started. That's more on the coding side. So if you're interested in hands-on coding, so it's called To Code AI. We already formed 5 groups, as you can see, from Longhorn, Warrior, and one is the Deep Doctor. So you can also join by yourself if you want to do, and we'll move from there. Our sponsor and partners, basically, we do have a non-profit here for Greater Goods Inc. That's how we're driving this meetup. And we have our sponsors for the venue, which is Capital Factory for today, and as usual, food and speakers, SparkCognition. So please give a big hand of applause for them. So quickly, the other stuff's just logistics, where you can get the Slack channels and other. I don't want to get into too detail. That's already you guys know. So with that, today is our special occasion. So we have with us Amir Husain, who is an award-winning serial entrepreneur, inventor based in Austin, Texas. He was a founding member of IBM Advisory Board for Watson Cognitive Computing, and is the founder and CEO of the SparkCognition, Inc., an award-winning company specializing in cognitive software solution that helps business and government better respond to the world of ever-evolving threats. And he's present with us today, and he's giving us this wonderful time for us to interact with him, and he will go over his book, The Sentient Machine, and it's in the tradition of Mikio Kaku's The Future of the Mind, acclaimed technologist and the inventor. Amir Husain answers the universal question of how we can live amidst the coming age of sentient machines and artificial intelligence, and not only survive but also thrive in this coming age. So we'll hear from him, and maybe we'll get some Q&A if he has time for us. And with that, and not much time, I would like to invite our special guest, Amir Husain. Please.
Well, fantastic. This is a great honor, and I'm thrilled to be with you. This is my first time speaking at Capital Factory. It's long overdue, so I'm glad we finally got an opportunity. The talk that I wanted to cover today is going to be inspired by the book for sure, but the book is right here, and what it says is available to you. But now that we're talking about it, I'd really like to build on some of the ideas that are in the book. Assuming that there is interest in some of these topics, we can use this particular venue to maybe build on these ideas and take them forward a little bit. So let me just tell you a little bit about my background. The interesting thing that you may find in this background is the fact that in addition to being an entrepreneur and having started several companies, SparkCognition being the latest one and fully focused on artificial intelligence, I've also been very interested in just fundamental computer science since day one, and that has been in many ways my calling in life. And so I serve on the advisory board of UT Computer Science, but then I also serve on the National AI Task Force for the Center for a New American Security in DC, which is a DC-based think tank that's trying to figure out how we solve problems around, for example, ethics in AI systems and how we deal with autonomous weapon systems and so on and so forth. And over the last several years, I've done quite a lot of work in this area. I also serve on the Council of Foreign Relations. So the three things here that you'll find is an entrepreneurial desire to convert the possibility of artificial intelligence into something we can use today. That's the engineering pursuit. The scientific pursuit of identifying where there are gaps, where we need to advance the science forward. And then thirdly, the policy aspects, the ethics and morality aspects, the legal aspects of these things that we're building. To what extent can we actually operationalize them in the world, and what are the various manifestations of these systems that we could build? So first of all, many of you might already know this, but I feel it appropriate to just clarify this point up front. When people think about artificially intelligent systems now, they generally tend to think of machine learning immediately, because that seems to be the dominant paradigm that almost everyone employs. But machines can think in many ways, and this basic notion of what thinking is in synthetic systems isn't bound to machine learning constructs and isn't bound to systems that learn only from data. So for example, McCarthy and Minsky did a lot of work with logic, and there are reasoning systems. If you're familiar with the language Prolog, it was built on constructs like that to be able to deduce and induce. There are, of course, artificial neural networks that are older than many of us might think. They go back really to the late 40s and 50s, the neural models that McCulloch and Fitts put together, and the work that came since. And then finally, genetic algorithms that John Koza really spent quite a bit of time developing. So the idea here is logic, where you have a series of essentially transforms that you can apply to a symbol set to yield other symbol sets that have meaning. So you have operators and operands, and the operands themselves are symbols which embody some fact about the world. And when all of these are chained and moved forward within the rules of logic, then you can lead to conclusions that might be valuable. And to the extent that those conclusions are perceived as smart, then that is a smart system. With artificial neural networks, the key thing to remember is that a neural network is a universal function learner. If you think back to mathematics and you think about the notion of a function, it has certain inputs and it has certain output, a domain and a range. But you specify what the function is, and so based on that function you can now graph it, you can plot it. A neural network is a machine that can iteratively conform itself to almost any function given enough data. So it's a universal function learner, and if you start thinking about it in those ways, then you realize essentially what's happening in a neural network. It's a different approach. Genetic algorithms are generative. So the idea here is that with a genetic algorithm, you're sort of mimicking biology, and you're using things like crossover and mutation. You start with monkeys on typewriters, and then you evaluate what they've done, and then you have some measure of goodness. It might be a proxy to goodness, but some measure of goodness, and you start to say, okay, well, this has a lot of potential. Let me mutate a little bit of it and see if the consequent generations, the follow-on generations, exhibit an even better fitness. I say this because I want to get across this notion that intelligence in synthetic systems does not accrue only from machine learning type systems. There are some that we know of, others that we will discover, many that will be hybrid. And while it is true that today deep learning and its various offshoots are delivering excellent results, a true artificial intelligence practitioner won't merely get hung up on that fact, but will try to look for value in all the various ways that we know of and many that we'll discover in future. So, as I said, deep learning isn't the only kind of AI, and what does deep learning do? We all know this picture. You provide lots of training examples of dogs and cats, and perhaps these are going into a convolutional neural network. And so a classification model that that network has learned will now take your input with the question mark, and will then, based on the training data, tell you whether the question mark ended up being a dog or a cat. Okay, so this is a classification problem. Neural networks can also solve regression problems or continuous value prediction problems, where the answer isn't yes, no, green, white, left, right, or center, but it's actually a continuous value. So okay, we can do this. The problem, of course, here is that we do require quite a lot of data. But now let's look at an example of a smart algorithm, an algorithm that can potentially beat a human being, but that requires no data. It requires no learning, and in fact, it never learns. So this is really an algorithm that is based on the idea of generating possibilities based on very simple rules, and then rapidly pruning those possibilities to then identify those specimens or those elements within this state space that make sense. And I'll explain this to you for a moment. So for example, consider the game of tic-tac-toe. At the very left, you have no marks. And then you might have two potential marks as the first move, indicated by the yellow square. And then the only thing you really know is that you can increment in each successive generation, one symbol at a time, and you know what the winning state, what the rules are for a winning state, and you also know that in every successive generation, you want to alternate symbols. So with these three simple rules, you can generatively produce the possibilities that exist in the game of tic-tac-toe. You haven't watched a single game. You haven't learned from anyone's input. You haven't done anything at all other than encode these three rules, and purely with generative techniques and a very small number of rules, heuristics to generate, you have an algorithm that can play a game. And if you make a mistake, we know that tic-tac-toe generally, if you don't make a mistake, will always end up in a draw. But if you do make a mistake, by gosh, this will win, right? So there are ways of doing things that are smart, that are human capable. It's as capable as a human. It can always draw at least. And this doesn't require any data. It doesn't require any learning. So it's another way of thinking about some of the problems that we might be overcomplicating with other techniques. So what is thinking? And I've thought a lot about thinking. In my view, thinking is the generation of ideas combined with pruning that happens in the brain. See, the reality is that we can consume about 20 watts of power. Our brain can consume about 20 watts of power. And the fact that we're able to solve very complex problems and the fact that we're able to pursue very sophisticated goals has less to do with what we can generate and more to do with the effectiveness of our pruning. Because if we were able to generate a large number of possibilities, the 20 watts computationally doesn't drive enough ability to really process each one of those possibilities and make a decision. So what's happening in the brain is that you are both generating and pruning at the same time. And in chess, for example, when you talk to a grandmaster, they'll tell you that no, we don't think about every possible move that you can make. When you're teaching a kid chess, you say, okay, well, here's the board position, and here's how this could move, and here's how that could move, and here's how all the moves could happen. But a grandmaster doesn't do that. They don't compute all the positions. They immediately and instinctively start to prune. And in that pruning, they buy themselves depth and direction towards a solution path, which is guided by a heuristic. In their case, heuristic, it doesn't look right. That just doesn't look right. There are some things that we know of, for example, control of the 4 central squares in a game of chess. Those are valuable. But there are far more complex and elaborate structures and positions that might make sense to optimize. So what is thinking? It's generating ideas and then pruning them. So with this basic idea, ideate and prune design, you can implement some simplistic game players, and then you can also do some sophisticated things. So if you have heard of this idea of GANs, generative adversarial networks, would you raise your hand if you've heard of GANs? Wonderful. So at least a third, if not more. You know, now that I've described this idea as generation and pruning, you see that that same template is what GANs are. And earlier I said to you that a neural network is a universal function learner. So what is a GAN? A GAN is 2 functions competing with themselves. One is generating and the other is pruning. And this is, to me, the kind of simplicity and elegance in ideas around intelligence that isn't spoken about very much. When you look at a common description of GANs, you immediately get straight into the sort of an egotistical treatise on how much math somebody knows. But the fundamental truth is a very simple truth. The fundamental principle is a very simple principle. And I'm going somewhere with this. One other thing that I'll say now, I think it's appropriate to say this. How many lines of code does it require, simplistically in your view, to implement a neural network? Does anybody want to take a guess?
How much
No, I mean, so how many lines of code to actually implement like back propagation and
Yeah.
very close. Yeah.
One
So
really well written line.
maybe in the right language that lets you cheat with syntax, but in general, I've seen pretty decent implementations that run like 9 lines, right? So, but that's not nobody carved that for me on a tablet, and I didn't bring that down a mountain. I'm sure there's a 6-line implementation, and eventually there'll be a 1-line implementation. But the point is, it's a trivial number of lines. Reflect on that, though, because as I really started thinking about that, it really started to change my view of a lot of our conceits in artificial intelligence. 9 lines of code embody a universal function learner. 9 lines of code. There is a lot of power and a lot of magnificence in simplicity. And when you start to see these things not as the labels that an academic researcher is ascribing to them, but rather in their essence, there is a new unlock that happens in your view of how you see artificial intelligence. Generating and pruning, universal function learners, GANs in that context, they become something quite different. And by the way, with this kind of capability in your head to be able to think about these problems in this way, this also is the root of innovation. Because if most of your mental capacity is spent just parsing the obviously difficult mathematics, you have very little time to actually think about the structural innovation. And my gut is that intelligence along these paths will be cracked more by structural innovation than mathematical trickery. So this design pattern at SparkCognition we've applied very heavily. Now we serve some of the largest companies in the world, so we have built in conjunction with, why doesn't this play? Is there a way to make it play?
It's not this big.
It's some of the work.
It's progressive. 2 or 3 slides down, I think. the
Okay.
simulation?
Whatever, I'll describe it if it doesn't play. So we've built systems, for example, that do that use reinforcement learning to build an autopilot, because we can't have pilots fly tens of thousands of times in every airport in the world. And for the first time, we've also been able to develop another parallel AI system that then determines when to abort a takeoff. This is a problem called rejected takeoff. It's a matter of life and death. You're hurtling down a runway at 120 knots. You have to make a decision split second based on the inputs you receive on the console as to whether you can safely abort a takeoff or whether you must first take off and then turn around and land the plane. You make the wrong decision either way, not good things will happen. So we developed the world's first AI system that first used an AI to replicate a pilot that could take off in every circumstance, in rainy runways, high altitude runways with varying pressure, snow, all sorts of things. And then we simulated failures of the left engine going off and the right engine going off and a partial failure and so on and so forth. And then, as using reinforcement learning, we set up the problem of, okay, now you decide whether you want to abort or whether you want to continue with the takeoff. To make a long story short, the results were that we were able to improve the accuracy of the decision, the quality of the decision, compared to the best human pilots. And we were able to cut down the time required to make this decision by 2 seconds, which is tremendous, because 2 seconds at 120 knots down a runway is many, many, many feet of runway that can make the difference between a safe abort and, God forbid, some sort of a collision. We've applied this technology to Deep Armor, our cybersecurity solution, which uses pure artificial intelligence and machine learning. The purpose of this platform is you can install it on your Mac, you can install it on your PC. I would encourage you to do so. And what it does is it can, without any signatures, it can identify whether the nature of a new file is good or bad, whether there are signs based on its past experience that this thing will do something wrong. Now, if you sort of reflect on this, how do we get data? Well, we get data because there are malware repositories and we get data from there. But we've also looked at ways in which we can generate malware-like data using artificial neural networks. So if you train up an artificial neural network on malware, and then you ask it to say, produce things that are like this, then you can start to do that. And if you have another discriminator that checks for certain conditions that, okay, you generated something that looks like this, can it also execute? Now you've created a generative adversarial network that can create millions and millions and millions of viable executable threats, which have different signatures. So this is already taking software engineering into a domain which very few fathom. A friend of mine who does database research was just recently shared a paper with me that indicated that the hashing algorithm that they've been using for many years in the database community to identify, how to map certain content to a certain place in memory, a certain place in structure. That was a very mathematical sort of a thing. You went through these algorithms, you developed the hashing algorithm, you came up with the formula, and that was the hash. Well, they've started using neural networks for it, and they've demonstrated that a neural network can learn a hash mapping function that is far more efficient than any known hash mapping function in database theory. So when you start thinking about that, these are fundamental components that make your computers work. We can replace these with these learning, neural functional modules. It's revolutionary. Now, there are problems. So what are those problems? The three big problems in machine learning right now is that you just need a god-awful amount of data. We try to predict when a large $100 million turbine will fail. Well, we don't have a million cases of a $100 million turbine failing. We want to predict when there'll be something wrong with a commercial aircraft. And thank God, we don't have 500 examples of commercial airline crashes, and so on and so forth. So how do we deal with situations where we have very little data. The other thing is that neural networks, yes, they are universal function learners, they can do a lot, but particularly when these networks get large, and I'm sure you know now that these networks are getting hundreds of layers deep, on the order of billion connections. These are getting seriously large networks. If you unfurl a neural network, what you see a vector of numbers, a vector of floats. That's what a neural network would be. And looking at that vector of floats, what could you make sense of, really? You couldn't really make any sense. It would be completely opaque. There would be nothing explainable. You wouldn't know whether this is an optimized network or a completely nonsense, randomly initiated network or a perfectly tuned network. So that explainability is very important. But the third problem, which I think is a big problem in artificial intelligence, is that with these networks we solve the problem of perception. We're doing very well at that, right? We're doing very well using networks to identify images, pictures, sounds, handwriting, all of these sorts of things. Now with, for example, SparkCognition working with one of the largest manufacturer of unmanned aerial vehicles, we're embedding technology that allows you to not only identify objects, but the entire pattern of life of that object over a period of time. So that's becoming very sophisticated. We can even predict things. As you know, there's research that's been done that can train up on a large number of videos and then can predict the current video 4, 5, 6, 7 frames ahead, up to a half second ahead. Okay, these are almost magical things. You're basically predicting the future with some reasonable probability. But there's still something missing, and that is intrinsic motivation. So the definition of intelligence is the ability to pursue goals. The greater the intelligence, the greater the nature of the goal that you can pursue. And at some level you have the ability to rewrite these goals. And at that point you are a great form of intelligence. So what propels you to change your goals? What propels you to get out of bed in the morning? What propels you to ask the question, what is my purpose in life? Because these questions may appear philosophical, but they are the starter fluid for the cognitive processes that drive you through the day and the week and the year and the rest of your life. And for an artificially intelligent system that can perceive, that can reason, that using reinforcement learning now can carry out action in the environment and can learn from the consequences of its action, why would it do anything at all? What is its intrinsic motivation? And the answer, of course, is, well, the motivation is simply, I've told it what to do. I've set an objective function, and the job of this thing is to optimize the objective function, in which case it is an entity that can never go beyond the goal that was prescribed. In other words, on the intelligence spectrum, it's fairly limited. It cannot improve its goals, it cannot change its goals. So this problem of intrinsic motivation and allowing synthetic systems to evolve intrinsic motivation and change their goals is something that I am very fascinated with and that I work on. So how do you deal with problems that need too much data? In practical situations, as I said, 3 of which are illustrated here, you don't have millions of examples of these sorts of things happening. So we've developed a number of techniques. So for example, we didn't have millions of examples of takeoffs in every airport. So we built an AI that worked in a simulation environment, and together we were able to demonstrate how we can use the data created by the simulators. On the left you have autopilot, and on the right you have autonomous pilot, the AI pilot. Notice that as they build speed, they're going down the runway, both the systems will encounter a left engine failure. Same situation, both of them. The one on the left, which is the current system that you fly in the commercial aircraft that you fly in, is having a very, very tough time dealing with this. It's already off the runway and the horizon line is going quite crazy, and you notice that the autonomous pilot is really maneuvering far more aggressively. So the range of its action is far more aggressive. The reason why we cut the video before we see the final result is because it's disturbing to some people. The technology that they use today, the one on the left, doesn't really make it. The autonomous pilot, however, can aggressively maneuver, and even if this particular situation on this particular runway hasn't been seen by it, it can still find its way out. Now, this, by definition, is a problem for which existing real-world data doesn't exist. So what we've done is we've run the world at machine speed and created a lot of data that has relevance to the real world. And therein become relevant areas such as transfer learning, which is that I have created data streams that are relevant within a virtual context, a trainer, a gym context, and now to translate those by means of some world error function to the real world. So if you think about every decision I've made in the simulator needs to be adjusted by some delta when I make it in the real world, then the collection of all such deltas over the collection of all such decisions you will make define the correction. They define the correction. And if you can learn the function that plots all of those corrective points, then you've learned the transfer learning corrective function. Could you use a neural network for that? And some people are trying to do that too, right? So you go from using and thinking about neural networks as this one thing, I train it and I put some data in and something comes out, to a new kind of software. And that, for software developers, should be revolutionary. I start many of my talks by saying Mark Andreessen said software is eating the world, and by that what he meant was that you could take a combustion engine which has thousands of parts and reduce it to an electric motor which has dozens of parts, and all the value of the combustion engine, like fuel flow, like speed control, etc., 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 those are still available in the electric motor, but they're implemented as software. The carburetor in an electric motor is software loops. The physicality of that system disappeared into the ether and was replaced with software. That is what is meant by software is eating it's physically eating the world. Software is replacing atoms. But my corollary to that is that AI is eating software. Because the way that we used to do software, we sat down and we hacked away at our keyboards and we created code and we wrote algorithms. And there are now multiple ways, one of which I described to you, another one is from genetics, where you can propose billions of solutions and set some constraint criteria to settle on a population of acceptable solutions. This is a totally new way of building software. So the other problem is that these neural systems are not transparent. You don't know what's going on inside them. So can neural pathways, so earlier I talked about when you take a neural network and you flatten it out like a vector, what do you expect to see? You expect to see a huge vector, a huge list of floating point numbers, right? Basically that's what it is, all the weights and so on and so forth. So inspired by the idea of an MRI on the brain, we started looking at whether there is something fundamental about just structure alone as defined by interweight relationships that could indicate whether a network was doing well or was doing badly. And while I won't get into all of this, we filed some patents around this as well, and it's complex. But let me give you a couple of base cases, which I think will start you thinking. So if I gave you a neural network that looked like this, it's very hard to say is this good or bad or whatever. But if I gave you a neural network that had all its values 0, and I said, well, what do you think? Is this a neural network that does something? Well, most people would say, no, it's a nonsense neural network. I mean, if I gave you a neural network that had all 1s, or that had alternate 0s and 1s, right? So the relationships between the weights matter. And that is in the fundamental intuition. If the relationships between the weights matter, why do they matter? What are the weights? The weights are, if you imagine this as plumbing, the weights are the flow controllers. And if in a graph-like structure where flow is important to arriving at an answer, the flow control is messed up, then that's one failure mode. So what we're trying to do is we're trying to take good networks, bad networks, sad networks, happy networks, small networks, fat networks, and we're training up other networks to try and recognize the characteristics, the structural characteristics of these neural networks. So if you will, an MRI machine for artificial brains, learning to spot structural problems. The third issue is a very interesting and somewhat of a spiritual issue of intrinsic motivation. So the problem with this sort of a question is that you can answer it as a software developer, and one way of answering this question is to say, well, you know what, let's not think about this much, let's have a random variable, and with this random variable, let's just mutate our goal every now and then. And that's one way of making sure that there's sort of some non-deterministic way in which goals are being changed. But they're to no end. Because from random goal mutation to random goal mutation, if truly the mutation is random, there is no story, there is no connectivity, there is no logic that carries that through. So fundamentally, random things cannot be part of the same goal. And when we do random things, we are then saying that the maximum level of the complexity of the goal that we can achieve is only one of these random instances. Three of them never will come together to tell a story. It will always be a TV show where every episode is standalone. It won't be a TV show that tells a story end to end. The randomness kills that. Okay, so what else could we do? Well, Andrew Barto, who is the father of reinforcement learning and just recently retired, and you know, here in Austin we have such an amazing group of brilliant AI people. One of Andrew's last students is Scott Meekum over at UT Austin, and he's a professor, he works at SparkCognition. He's one of the best reinforcement learning guys out there. And Andrew's group for a long time, and Andrew's now retired, but Andrew's group for a long time contemplated this notion of how do you get machines to act with agency? What is intrinsic purpose? I don't know that there are answers to this, but I think one clue that we do have is that whatever this purpose is, it is emergent. And emergent in the sense that we have certain urges when we're born. We want a bottle of milk, and we want the comfort of our mother, and we have these very basic urges. They combine and conflate and create complex needs. And this process of conflation and combining across both temporal and spatial axes causes an emergent complexity of emotions, which are then tied to purpose. Okay, this is one functioning theory. So of course, we're interested in this. And one of the things that I want to figure out is, if we can't do AGI right now, how do we build, some have theorized in the AI community, well, what if we could start with a 2-year-old child? What if we start with a 3-year-old child? And then maybe teach that child enough. In fact, here in Austin, many years ago, 40 years ago, there was a push for an ontology system called Psych that would encapsulate all of the common sense in a logic programming language, and that didn't really succeed simply because we found that there was a very large collection of facts that comprised common sense, and that these facts were very difficult to encode. So the way that I think about this is, you start with the child not at the age of 2, but the second it's born. And you know a few things. One thing you know is that this video is hard to play. So you know a few things. You know that there is a hunger level, and the only action that the child can really take is either cry or flail. You also know that their vision is highly undeveloped and they can only see black and white, roughly like this. So the mother engaging with the child with a bottle is seen by the baby just with these pixels. And the hunger level peaks the crying peaks because there are just two actions, left and right, cry and flail, that the child can do. So in a reinforcement learning type methodology, what's happening is the child is first saying that which moves together is one thing. So the things that are moving together, object A, let's not call it mom yet, but object A is a thing. Things that move together are a symbol, and I can refer to them subsequently as a symbol. Oh, and look, this bottle, even when she is static, these pixels for the bottle, they keep moving, so that must be another thing. So that is a thing B. And it's interesting that when I am shown A and B, suddenly my hunger level goes down. So this is an example of a basic convolutional net identifying through a very simple heuristic that which moves together is one thing. You don't have to name it because you can tag it with a symbol. And you measure the concurrent appearances of these objects. The only thing you can do as an action is cry and flail. So for example, you cannot see A, you cannot see mum, you cannot see B. You're alone in the room, hunger levels high. You flail. You flail, and you flail. The hunger level's still high. So that's a failed strategy. There's one other thing you can do, which is cry. And maybe you cry and flail. And suddenly when you cry and flail, you see two things. One, you see A rushing into the room, and then your expectation is that 90% of the time when I see A, within 3 minutes I also see B. So then you calm down a little bit, and then B appears, and your hypothesis about the appearance of B and A being an agent to deliver B is fulfilled, and your hunger level goes down. So these are very simple relationships, but you can see how logic can be constructed with no prior knowledge other than a few seeded heuristics. And once you start to do object identification and you start to marry object identification with symbolic computation. On my first slide I said there's logic, there's neural networks, there's genetic programming. So where does genetic programming come in this? Of course, I won't get into this now. This is my last slide. But the other thing that we're looking at is that in the cerebral cortex, what we do is we do projection, we do prediction. And one of the things that we want to do is, for lack of a better word, identify these objects, identify their relationships, identify their probabilities, and then Monte Carlo them. Now I know the human brain doesn't necessarily Monte Carlo things the way that a computer does, but these are essentially pruned rollouts. If I invite Fred, and I invite Tom, and I invite Sandy, will that make for a good party? Right? And that's based on some experience. That might be based on you playing in your head. You may never have invited those three people together, but you may know some facts about them that you surmise and you project and you say, that's probably not the right thing to do. So that then is the second part of this, which is the predictive element. Now, if we can get to the point where we do basic object detection in this way, we start to construct logical relationships between these, and we tie these logical relationships to a limited set of actions that a small, under 6-month-old child can then can do. And we start tying these together. What I expect is that you will see the learning, not the brain of a child, but the learnings of the brain of the child start to show up. That'll be interesting. And this is the kind of characterization of intelligence which is appealing to me, because it's not that we will take a brain, chop it up into 5 billion slices, take pictures, and then replicate it exactly the way it is without fully understanding all the connections, and then if we glue it back together again and we put 12 bolts and bam, it'll start working. I mean, of course, I'm being facetious. There's a lot more that goes into that, and very brilliant people like Henry Markram in Europe and many others are doing whole brain emulation work and so on. But to me, my feeling is that what ultimate secrets we find in intelligence will be simple. Going back to 9 lines of code gives you a universal function learner. 9 lines of code. Maxwell's equations are not that voluminous. E is equal to mc square encapsulates a big chunk of physics. The Newtonian mechanics formulas are small, a few characters, and they encode so much universe level behavior, not even localized behavior. So we have some examples from the natural world that suggest that brevity and simplicity can often be at the root of a very complex phenomenon. By the way, what is computation in this sense? Computation to me is the magnifier that takes the seed of mathematical simplicity and grows it into the kind of complex interaction and the complex things that we interact with in the complex world. Computation is the vehicle, computation is the magnifier. So rather than get caught up in the computational machine, one gets maybe thinking about the representation, and in thinking about the representation, perhaps we see things that others might not. So with that, I will stop here and see if there might be any questions. So,
I don't know if I can properly articulate this, and I'm probably the dumbest person in this room, but if we train these machines to observe the world around us, and they start detecting things that we can't see, do they then become kind of the translators for other dimensions?
well,
And I'm thinking of things beyond, like, you know, when you get to the far ends of the spectrum and
sure.
all these things you can pick up with infrared and et cetera.
Well, infrared light exists in this dimension. Ultraviolet and audio frequencies that we can't hear exist in this dimension. You know that certain animals, dogs for example, have a slightly shifted audio range. So the realities of various different animals are different. You've seen pictures perhaps in science books that show how the compound eye of a bee forms an image of reality. You know, it's very, very different. And that's the only reality the bee knows. Thousands and thousands of kaleidoscope-like small pictures that all come together, they're all repeated, slightly different angular offsets. Now, when that is the only way you've seen the world, is your world model different? Of course, of course. I don't know, however, that I would be so fast to jump to the conclusion that it is a picture of another dimension. I would say that it is another way to form a subjective reality, most certainly, but not necessarily another dimension. Now, if you had a sensor, an artificial sensor, that you augmented your eye with, whereby you could see, say, energy being released from another dimension, which I'm not a physicist. I would have to ask my older sister if this is practical, because she is one. But let's say that such a sensor existed, then yes. But I think for the types of things you're talking about, you're not talking about dimensional issues. You're talking about an alternate subjective reality based on the kind of visual and audible stimuli that an ordinary human does not get.
Thank you.
I'm not asking a question, I'm just asking.
Okay, thank you. There's a question. Okay.
Why is explainability important?
Explainability is important because last night I was in DC and I was at a dinner. I was speaking about these topics, particularly in the context of autonomous weapon systems. And we had Deputy Secretary Bob Work, who's done a lot of work in this area. We had 2 vice admirals, General representatives from all the major defense companies, and many others. And the core issue was one of, for competitive reasons, we understand that we have to implement this technology and we have to invest in this technology. But delinking the action of taking a human life in a way that a human being is not at the other end and doesn't feel the subjective feeling of having killed someone, is that morally, ethically correct? Should there be a system that takes a man out of the loop completely? And connected to this is the issue of, if an artificial intelligence system is giving you a recommendation to kill, this is the most extreme example, but there are many examples, to fire, to arrest. Like in China, they've now deployed a social credit system, and under the social credit system, if you are late to pay your bills, if you have a government job and you don't do a good job and you show up late, if you go past the red light, if you are caught outside a house of ill repute, etc., 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 all of these things are counted and they deduct from your social credit score. And this is a social credit score that the government now keeps on you. This is not fiction, it's happening today. And so you might board that flight from, Xinjiang to Shanghai and find that you are no longer allowed to board the plane. You may apply for a job and you may find that your social credit score disqualifies you from a job of this level. Now, it's one thing to think about the impact or the society that would enable such things, but set that aside. Even if they choose to do that, let's hope that they use the right findings and not the wrong findings and not defective findings. So even in that context, explainability is very important. An artificial intelligence system is telling you that I think Bob is untrustworthy. You shouldn't just say, okay, black box, thank you for telling me Bob is untrustworthy, off with his head. You don't want that. What you want is, okay, black box system, would you explain to me why Bob is untrustworthy? And then the system starts to give you a lot of evidence. So it works back from its conclusion to give you its reasoning process. This is very important.
I can see why accuracy would be important.
Yes, but accuracy is measurable only post facto.
True.
When you have a large amount of such calls being made. In the evolution of human history, there is comfort to be derived by providing some argument before you act on the end recommendation, and that argument is actually embedded in the process of jurisprudence. If you just presented all the facts to the judge, and the jury and the judge sat down and said, data this, data that, nobody needs to argue a case, nobody needs to tell a story, made decision, bam, done, off with his head. But that's not how it is. The way it is that you get an opportunity to reason through the data, to tell the story, to convince yourself that what you're seeing in the data is accurate. Well, this is a kind of system that has evolved in a similar way across all human societies. Now, over time, we also know that there are so many cognitive biases that we suffer from. Judges, before they are ready for lunch, they are deprived of glucose, and it's a certain kind of glucose that's very necessary for making decisions. And so what they start to do is, this was a study done in Israel, that they start to reject bail applicants just randomly. The rate of rejection on bail applicants goes up tremendously. Parole applicants goes up tremendously. And then when they've been satiated, they come back, and if you were lucky enough to be the first or the third after they got that quart of vanilla ice cream in their belly, then you're lucky. So, this is somewhat comical, but somewhat incredibly tragic, because the human condition is made up of millions of such completely random things. The random variable of when his lordship has consumed his ice cream, and where in that stack your application was, could change your life. So People like me that think about artificial intelligence and think about ways in which we can improve human decision making, think about things like that. But there are other counterpoints as well, which say, well, you dehumanize the process. To me, I'm like, what does that mean? What does dehumanizing a process mean? Does it mean you're removing human biases from it? But, you know, the thing is, after I wrote The Sentient Machine, I showed up on a right-wing, religious website that quoted passages from the Bible and said, you know, this is the work of the devil. I've been sent several notes that, threatening notes, one of which was, skin you rich. Other quite vile sorts of things. This is obviously a topic, so what I take from that is this is a topic that's very relevant to a large number of people. Because in artificial intelligence, they see their own worth potentially evaporating. And if you then also say that, by the way, I'm going to make all the decisions for you, and you will never know the reason. The black box said, you're in jail for the next 30 years, here's the door, throw away the key, see you later. That then is, from a social perspective, a disaster.
The other question.
If we look at neural networks, my understanding is that the name neural network comes from the graphical representation of that model, being suggested of the structure of the human brain, but in fact is very different from the way the human brain works. Do you see the future of having artificial intelligence that's most like the human brain being a continuous evolution of neural networks, or something entirely transcendent?
A thought experiment. I said that neural networks are universal function learners. Let's say that in the future, 30 years hence, we build an artificial neural network system that learns the function of someone's brain and starts to exhibit equivalent action to that person. Once the system has learned that function, could you then extract that function? How would you extract that function? You would take a large number of domain values, get range values, and from that reconstruct the function that the network has learned. I'm simplifying this, but the point is it's within the realm of mathematical possibility. It's a thought experiment. So now that you've extracted that function, is there an alternate way in which you could implement that function again? Of course. So what does that tell us then? It tells us that the uniqueness of the human brain is it's a very efficient computer and learning system that has learned one, maybe multiple functions. But what they are fundamentally functions. So the issue we're having is how do we get to those functions? But once we get to those functions, we will find that there are many ways to implement them. This, by the way, is something that we've seen in almost all other technological innovation that draws upon nature, some natural inspiration. We build forklifts, but none of them look like elephants. We build jackhammers, but none of them look like gorillas. We build tanks and APCs, but none of them look like chariots or lions or tigers. We build aircraft, and none of them look like birds. So the fact is that the partial similarity between the structure of the ANN, artificial neural network, with some parts of the brain, has been shown to be sufficient for this abstraction to be a universal function learner. And of course, there are many parts of that complexity that are totally lost, not just the volume and the scope of the connections, but for example, glial cells. We've talked about the axons, we've talked about the neuron, we've talked about dendrites, but these all swim in a sea of glial cells, and in the original models, these were essentially said to be essentially not doing much. But what we found now is that there is actually some change in potential and some communication and some interaction that these glial cells do engage in the brain. And the artificial neural networks that we use now don't have an abstraction for these glial cells. The closest you could do is you could say, well, I'm going to add another weight called G, and whatever the effect of these glial cells will be to my activation function, I'll try and see if, along this sort of linear slide, I can get close to it. So I'll try and see if something like that changes things. But when you do something like that, you realize that you're back to pretty much what you had. Because by adding another weight, what you're doing is you're just saying two numbers get added. You already had that one number. You could have just spanned that number over a longer range. So, yes, but the net result is that even the abstraction is capable of learning universal functions.
Back to the point. You mentioned an example about that airplane that there was limited data, that the number of synthetic data or whatever simulated data was generated. That was a great example of validation of any practice in artificial intelligence model development. So we can always generate any number of data that we need, or any circumstances could be simulated. It used to be with multimodal simulation, for example, in the past. These days, AI is dominant methodology. So where we are, or at least in practice, these models which are generated today, in terms of validation of these models, in terms of technical validation, functional validation, or maybe ethical validation of these models, I believe, this is my perspective, I want to know your thought about that. An appropriate validation practice on any type of AI model would solve a lot of these challenges that we have today. What do you think about that?
Well, I think it's sort of a tautological question, in the sense that what you're saying is, if we could solve these, then they would be solved. Because the way that I've understood your question is that today we learn certain models. These models and actuality have some delta. And if we were able to figure out how to bridge that delta, then we would solve the problem. I agree with that. But I don't know that that gives us any additional insight compared to where we are. This is very similar of a formulation as the transfer learning idea that I was describing to you. And the other thing is that the reasons why you have that delta may not be very important, because as they say about the financial markets, people will come to you and they'll say, well, this stock will go down because the CEO is really, going crazy and he's saying strange things on Twitter, and the banker is going to pull his loan and this and that. So there's 20 factors, but the net result is that the manifestation of all those factors is all encapsulated in one variable, which is the price, right? So in this particular case, the reasons why there are deltas may be 27 reasons, but the manifestation of all of those 27 reasons will come down to one thing, the delta. And if you can learn that delta function, then you've learned the way to transfer knowledge acquired in a simulator and apply it in the real world.
Okay, I guess we can take another question. We have a couple of questions online, so I just want to make best use of this one.
This is a little simpler, less philosophical, but back to explainability, and I also see that kind of goes together with fitness in some ways. Like sometimes you just have to accept that you can only understand fitness. And I've done some abuse and misuse of ImageNet, and came to the conclusion that you could decide if it was going to give a good result by really deeply inspecting the activation at the third and last convolution layer. And so you basically, if the network's training didn't develop good features on a given image, your output's basically random. So you're fairly early in I can't remember, 22-layer network. tell from that one layer pretty much if you're going to get a good result out the back. I was just wondering if you got similar things in pure neural networks for fitness. You talked in general that, about connectivity, but have you found that there's a point, a heuristic for, where to look for whether a network is properly trained instead of just across the entire network?
Yeah, so there's some work being done now by LeCun and also Hinton. They're going in a slightly different direction because their direction, like what you're suggesting, is focused on one class of problem. And this whole idea of first training a network and then chopping off the last layer or two, the decision layers, this is a practice that they use as well. And they use it in a different way, which is to prime the early layers of a network to a set of weights that get it in the rough ballpark. And then they add some final layers, and then with a small amount of data, they can get the network to perform a lot better than it would with just that small amount of data. Okay, so there are many such things that can be done. This is again one heuristic to basically say the data that I gave, is this appropriate for this problem class? Because if it didn't allow me to use a small number of additional samples and get to a reasonable answer, then it probably wasn't, right?
Yeah, so I have a comment on that general class of papers. I've seen a number of papers on that. And I think many times the motivation of the authors is they don't have the money to do training, but they want to do something in publishing paper.
It could be, but we deal with the DoD, and it's not just about the training and so on. It's also that it takes 2 years to get an individual security clearance. It takes about that time to get a facility clearance. Then you got to invest in a skiff. Then you got to be on JWICS. And before you do any of that, you can't get any data. And even then, all the interesting data is compartmentalized. So that's another few years. And in the world of machine learning, 4 years is an eternity. And so if you want to be practical about this, you have to identify similar situations. You have to say, I've got to make a difference in these situations. It's not about I don't want to train. We work with one of the largest banks in the world, and they are not able to share deal data. They want us to ingest deal data, but they can't share the deal data with us. And it's compartmentalized even within their own organization. So we have to then create synthetic data that kind of looks like the deal data. And we do a lot of that and pre-train a model, and then it's ready to go, and then they add a little bit, and then hopefully it gets there. So the motivation for this is not merely that they don't have the money or they don't want to. Data governance is in the practical world, it's a big problem.
Yeah.
Yeah. Please.
Okay, so this will be the last question we take, because we need to have the book signing going. So.
Okay.
I just had a quick question as far as where do you see AI in medical? I know there's a lot of research out there and things like that. Where do you see it going?
I think there's tremendous potential. In the book, there's an entire chapter, and I also talk about some of my own long-term ailments, which, frankly, I think can benefit from additional developments in this kind of technology. So I think it's a massive potential. Early on, IBM Watson and some other products have been applied to things like cancer diagnosis and so on, and there's been some mixed results. But the press usually takes things that they don't understand too deeply. I mean, they don't understand the deep science of AI and exactly where these things are, but they hear a story here and a story there, and says, well, out of these 5, 3 didn't work, so therefore it must suck. These guys are all idiots. That's not so simple. You're developing a revolutionary new technology, you need time. So I think that my view is I'm very optimistic. I think AI will apply to the medical community all over. I'm particularly excited about the results that were seen in Japan, where, for example, using neural networks and actually EKG, MRI data, they were able to recreate dreams, live dreams. I've been very encouraged by the interpretation of signals from severed limbs through neural networks that were able to decode the remaining electrical impulse at the end of that severed limb to then drive a mechanical limb. These are direct applications of neural networks. I think that in drug discovery, genetic algorithms will play a huge role. I think in curing bucket illnesses, which is one name for 500 illnesses that nobody understands, so they say, hey, why don't you just take some steroids? Why don't you just take some X big, bucket medicine? Because frankly, we don't understand what the hell you have, and we just call all 500 of these illnesses by one name. There's a very interesting section actually in the book that is a dialogue between me and my doctor as I suffer from a condition that plagues me. And so I'm very optimistic about that.
With that, before wrapping up, we have a number of online questions, but just I'll take one soft one. How do we need to adjust the way we are teaching children from an early age in order to prepare?
So I dropped out of school when I was in grade 8. I took my, in the British system, I took my O and A levels privately. I joined college at the age of 13. I graduated at the age of 15. I am not a conventional student. I think that a lot of conventional school is valuable in that children learn how to survive with other children. But if you look at school as a place of learning, then my God, I don't think that's a really effective characterization. I think parents are responsible for ensuring that their children become lifelong learners. I think that that involves both discussion and it involves hands-on work with them. It's very, very difficult, but it's the biggest thing you can do as a parent. And if you can't do anything else, if you can just expose the child to enough to where you see the spark in their eyes of them having found a passion, your job is done. Because then that brain, which is much younger and much more pliable and much more powerful than yours, will take over and it will create its own future. But your job at the very minimum as a parent is to expose the child, encourage the child, and give them that one thing that can spark their imagination. You do that, you've done your job. It's pretty simple.
So with that, we want to conclude this section of the speech, and many thanks to Amir and SparkCognition for getting it done here, and we're really grateful for that. And after this, we'll have a short book signing ceremony. So please get your copy if you have already. Get it signed with the author, and he's giving the time to do that. So
thank you.
Take advantage of that. Thank you.